look at limits involving infinity. And we have two different objectives. The first is to determine infinite limits from the left and from the right. The other thing we want to do is to find and sketch vertical asymptotes, which we've done before, but we're going to look at a more formal definition of the vertical asymptotes. So the first thing we need to realize is that a limit which increases or decreases without bound is called an infinite limit. And we've kind of touched on this topic as we've gone through limits, but we're now formalizing it a little bit more. So let's take a look at this graph of f of x, where f of x is equal to 1 over the quantity 2 times x plus 1. So first we're going to look at the limit as x approaches -1 from the right. And we see that our y values are approaching infinity. Then we will look at the limit as x approaches -1 from the left. And we see that our y values are approaching negative infinity. Because these are not approaching the same value, the limit does not exist. But this function does have a vertical asymptote at x equals -1. Now we're going to look at our second example, but we're going to do it algebraically. So we need to think about what happens as we approach different values of x and substitute them into our function. For part A, we want the limit as x approaches -1 from the right. So what we're talking about are values like 0.9, 0.99, those types of values. If we were to substitute them into our function f of x, our numerator would be approaching 2. But our denominator, when we square 0.9 or 0.99, those values are close to 1, but less than 1. And then if we subtract the 1 here, we're approaching a small negative number. Well, 2 divided by a small negative number becomes a really, really big negative number, also known as negative infinity. Now we're going to look at the limit as we approach -1 from the left. So these are values like -1.01, -1.001, and I should have put negatives on those. So again, our numerator is going to be approaching 2. In our denominator, if we square these values, we'll get a value larger than 1, and when we subtract 1, we'll end up with a small positive number. 2 divided by a very, very, very small positive number means that it's going to be a very, very big number, but also positive, so it's approaching infinity. Since our limit from the left doesn't equal our limit from the right, then the limit as x approaches -1 does not exist. Now we'll look at the limit as x approaches 1 from the positive direction. So these are numbers like 1.1, 1.01, etc. If we were to substitute them into the function, then our numerator is going to be approaching 2. And our denominator is going to again be a small positive number, which means that the limit as x approaches 1 from the right will be infinity. And then finally, if we consider what happens when we look at the limit as x approaches 1 from the left, our numerator will again be 2, but our denominator will have a very small negative number, which means that this will be approaching negative infinity. So because we're approaching infinity and negative infinity, we know that there are vertical asymptotes at x equals 1 and negative 1. And this is actually a theorem or a definition that we can look at down here. It says that if f of x approaches infinity or negative infinity, as x approaches some number from the left or the right, then the line x equals c is a vertical asymptote. And then there's the theorem that goes along with it, which basically says that if there are two continuous functions in an open interval containing some c value, and basically f of x doesn't equal 0, but g of c does, then there is a vertical asymptote at x equals c. And we can go back and look at example 3 to kind of confirm this. We know that our denominator is going to equal 0 at x equals 3. We can either sketch a quick graph or we can think about this numerically if we approach from the left and from the right. I'll sketch a quick graph because we've been doing so much of that. A horizontal asymptote at y equals 0. A vertical asymptote is at x equals 3. The negative 7 flips us over the x-axis. The squared means that both curves are headed in the same direction. So here's our quick graph, which means that our limit is going to be approaching negative infinity because we're approaching the same value from the left as from the right. Okay, now we want to determine where f of x equals the cotangent of x has vertical asymptotes, which is essentially when we're approaching positive infinity or negative infinity. And there are a number of ways to think about this. We can think about that fact that f of x is the cosine of x over the sine of x. So we could consider where or for what values sine of x equals 0. And we know that that occurs when x equals 0, pi, 2 pi, 3 pi, and on and on and on. So that means that f of x equals the cotangent of x has vertical asymptotes when x equals n, not m. Let me erase that for you. N pi. All right, now I want you to take 3 or 4 minutes, 5 if you need them, to think about these 4 functions and the limits that I'm asking you to find without a graph and without Desmos. So what happens if you plug in a really, really small positive number, a really, really small negative number, a number that's getting closer to 1 from the left, closer to 0 from the right, that kind of thing, and see if you can logic your way through this. Once you're done with that, then we'll go over the answers. So hit pause, and then we will talk about the results. All right, so let's consider our results. For the first example, we have the limit as x approaches 0 of 1 plus 1 over x squared. So since it's an x squared, we know that as we approach from the left and as we approach from the right, we'll end up with a very small positive number. 1 divided by this small positive number means that this whole term is approaching infinity. 1 plus infinity is still infinity. Okay, for part B, we want the limit as x approaches 1 from the left of x squared plus 1 over the cotangent of pi x. So the numerator will be approaching 2. The denominator, we're looking at the cotangent of pi x, well really the cotangent of pi, So if we think about our cotangent graph, here's pi, here's 0. Oops. We know that cotangent kind of does something like this. So our denominator is approaching negative infinity. 2 divided by a really, really big negative number is going to be really, really, really small. So small, it's essentially 0. All right, now we can look at the limit as x approaches 0 from the right of 3 cotangent x. We can go back and look at our cotangent graph, and as we come at 0 from the right, we can see that the y values are approaching infinity. All right, and then for our last example, we have the limit as x approaches 0 from the left of x squared plus 1 over x. So when we come from the left, we're talking about very small negative numbers like negative 0.1, negative 0.01, negative 0.001. If we were to plug these in for x, then the x squared would make these positive, but even smaller. So we're essentially approaching 0 here, plus 1 divided by a really, really small negative number. And so that means that we're approaching negative infinity for that term. 0 plus negative infinity is still negative infinity. All right, let me know if you have any questions.